Science friends. Today we are talking about reversible reactions, okay? But before we get into reversible reactions, I want to talk about the reactions that you already know. So in the past, the types of reactions that we have learned about were called irreversible reactions. So in an irreversible reaction, you have something like NH4Cl, which is ammonium chloride, and it breaks down into ammonia and I kind of messed that up, and hydrochloric acid. Okay, that is an irreversible reaction. You start with NH4Cl and it breaks down, and when you get your NH3 and your HCl, then you're done. It's complete, it's a complete reaction, and it's finished. Okay, we have also very briefly talked about one other type of reaction, which is no reaction. If you remember, we talked about those when we talked about aqueous solutions. Remember, you would have to break down your aqueous solution into spectator ions, and then those spectator ions sometimes would all cancel out, and you would end up with no reaction. So sometimes you'll mix two chemicals together and nothing will happen. There's no product detected, and so that's a no reaction. So today, what we are focusing on is kind of the middleman that bridges these two reactions, and it is the reversible reaction. So in a reversible reaction, instead of having this arrow that goes in one direction from the reactants to the products, you have this special arrow that looks like this that shows that that reaction proceeds in both directions simultaneously. So we say that it happens in the forward direction, but also in the reverse direction. So the forward direction would be like in this reaction if we converted NH4Cl into ammonia and hydrochloric. The reverse reaction would be if we converted ammonia and hydrochloric acid into NH4Cl. Okay, now not all reactions do that. That reaction actually doesn't do that, but some reactions do, such as this one diagrammed in the picture. N2O4 is converted into NO2. Now, what you may realize in this, and I didn't realize it quite at first, but there are two molecules of N2O4, and there are 4 molecules over here. And so in the equations, you see that they've basically simplified it. So they've left it as a 1 and a 2 instead of a 2 and a 4. But it's just a simplified version of that picture that's drawn. But in this first reaction, this first box that you see, we see that N2O4 is the reactant. This big guy here is the reactant. And these little guys over here are the product. But over here on the other side, they've switched places. These little guys are the reactant, and the big guys are the product. And that's what we see in a reversible reaction. The reactants can become the products and vice versa. Okay, so you'll start at the beginning with all of your reactant, and it'll start to turn into product. And then as that product starts to accumulate, it will go back and switch back into the reactant. Okay, when those accumulate and the other runs low, then it will convert back to the product. And so that's what's known as a reversible reaction. Okay, now in a reversible reaction, one of the goals is to get to a state of chemical equilibrium. So in chemical equilibrium, the forward reaction and the reverse reaction take place at the same rate. Okay? There's that term rate that we learned about yesterday, which is just kind of like the speed. Okay? So let's look at this diagram of this water faucet to kind of use this to explain it a little bit better. All right. So in this picture, we have 2 different spigots that are being used to fill up this container. So what would happen if we turned this spigot on high? We opened that one wide open, and we had this one on low, just barely opened it. What would happen to the water in that tank? Well, you should say that the water level would rise, right? This reaction is proceeding faster than this reaction. And so as a result, the water level would rise. Now, if we switched it and we had this one on low and we flipped this one to wide open, then there's going to be a lot more water going out than water coming in. And so instead, the water level is going to drop. All right. Now, if we put them both on medium and they're bringing water in at the same rate, okay, the forward reaction is the same as the reverse reaction, then we would expect the water level to stay the same. And that's what happens in chemical equilibrium. They end up having the same rate. The forward reaction and the reverse reaction are the same. And so there's no net change in the components of the system. There's no change in the water level. Now, when we talk about the components of the system, what we're really talking about is our reactants and our products, okay? In a system is just referring to anything that's involved in that chemical reaction, okay? So, one thing that's important to note, though, is that at chemical equilibrium, just because the rates are the same, as you see here, the forward rate levels out with the reverse rate, and we have equal rates. What doesn't have to happen is the concentration doesn't have to be the same, okay? Here we see there's a lot more of whatever this blue guy is, and a lot less of the red, okay? We also saw that over here. We had 4 molecules of NO2, but only 2 molecules of N2O4. But those could still be at chemical equilibrium, even though the concentrations are different, okay? So that's important. Now, this type of chemical equilibrium is also a special type of equilibrium known as dynamic equilibrium. And what dynamic equilibrium means is that it's always moving. It didn't stop, okay? In this example of the water level is the same, but the faucets are still on. Water is still moving. It's just not moving at a rate which it's going to cause anything to change. And that's what we mean by dynamic equilibrium. It's still moving. It didn't stop, but it's the same in the forward and same in the reverse. Okay? So, let's move on. So again, the equilibrium position is that point about right here on the graph where the concentration of the reactants and the products is no longer changing, okay? Now, before you get to that equilibrium position though, sometimes you have reactants that are favored. Sometimes the reaction is proceeding in the forward direction more. Sometimes the reaction is proceeding in the reverse direction more. And so that's what we see here in this first picture. In this first picture, this reaction is, we use the term favoring. It is favoring the formation of B, okay? 80% of it's being converted to B, only 20% to A, all right? Now, eventually it might level out once it gets to that equilibrium position, but right now we're forming more products than we are reactants. We haven't gotten to that equal level yet, okay? Versus down here, A is favored. There's more B converted to A than there is A converted to B. And the size of the arrows indicates that, okay? Now, one other thing that's important to note about equilibrium is that if you have a catalyst at chemical equilibrium, it's going to work on both the forward reactions and the reverse reactions equally. Catalysts do not favor one reaction over the other. It works at them both equally. Okay? Now, let's really get into the meat and the potatoes of today's lesson. So this is what your assignment for today focuses on, and that's Le Chatelier's principle. So Le Chatelier's principle tells us if we have a system, so again, that's our reactants and our products that are at equilibrium, if they're at dynamic equilibrium, but you do something to change that system, it's going to cause the equilibrium to shift. They're not going to go 50-50 anymore. One of these arrows is basically going to get longer than the other, and one of the components, either the reactants or the products, are going to be favored. Okay? So what are those changes? What are those changes that can cause this shift to happen? Well, these changes are sometimes referred to stresses, but they include a change in concentration of reactants and products, a change in temperature, or a change in pressure. If you change any of those things in a system in equilibrium, it's going to cause the equilibrium to shift. All right? Now, let's explore this a little bit further. So let's look at concentration first. So let's just read this together. It says, if you increase the concentration of a substance, it's going to shift the equilibrium away from that substance. Okay? So this example says adding HI. Here's our HI. So if we add more of it, it says if we increase the concentration of a substance, it's going to shift our equilibrium away from that substance. So that means our equilibrium is going to be shifted to the left. HI is here on the right. So the equilibrium is going to move in the opposite direction. It's going to go away, so it's going to go to the left, or we could say to the reactant side. Okay? Now, on the flip side, if you decrease the concentration, it's going to shift the equilibrium toward that substance. So let's say instead, what if we decreased the concentration of H2? Okay? So basically what that's saying is I'm kind of starting to run out of H2. Well, if we are trying to get this back in equilibrium, what do we need to do if we're running out of H2? We need to make more H2. So guess which ways the equilibrium is going to go? It says decreasing the concentration is going to shift it towards that substance. So if we lower H2, it's going to shift towards the H2 to try to make some more H2. Okay? Just to revisit the HI. If we increase HI, if we have too much HI, that HI instead is going to be used to make more H and I. Okay? And so that's why it's shifting this way. We're trying to balance it out. The goal is to get to equilibrium. Remember what that term means. It means balance. It means same. Okay? And so think of what that looks like. All right, excuse me. Let's take a look at the next part. The next stressor is temperature. Okay? Now, to understand temperature, there's a little bit of background information that you need to know. We haven't done our thermodynamics unit yet, and this is something that we will cover in more detail there, but I'm just going to kind of give you the basics so that you know enough to use it with Le Chatelier's principle. So, all reactions are one of two types. They are either an exothermic reaction that release heat, okay? So in an exothermic reaction, you have your reactants, yields, products, plus heat. So the heat is on the right side of the equation because heat is released, okay? Versus in an endothermic reaction, you have your reactants plus your heat yields products. So over here, the heat is on the left side of the equation. Exothermic reactions release heat, so it's on the right side of the equations. Endothermic reactions absorb heat, so the heat is on the left side of the equation. Exo, heat is trying to exit, so it's on the right, on the product. Endo, heat's trying to come in, so it's on the left, it's on the reactants, okay? Remember that. Now, exothermic reactions have a negative delta H. Now, you don't really have to know what delta H is. Delta H is the change in enthalpy, but you don't have to know that right now. But you just have to know that exothermic reactions have a negative delta H, okay? Endothermic reactions have a positive delta H, okay? Now, let's take a look at this reaction. It's not listed on here, but the delta H of this reaction is positive 187 kilojoules. So because it has a positive delta H, we would say that this reaction is endothermic. So what that means is that the heat is on the left side. It's absorbing heat, okay? Now, that's our basics. That's what we got to know to work with this. So let's read what it tells us. It says, increasing the temperature causes a shift away from the source of the heat. Decreasing the temperature causes a shift towards the source of the heat. Okay? All right, so in this reaction, the heat is on this side. Okay? So if we add heat, what that means that we're going to add the heat on the other side. Okay? When we add our heat, we always basically move it to the other side. All right? So now it is going to cause a shift away from the source of the heat. So it's going to move away from that heat, so it's going to go to the left or to the reactant side. Okay? I think the heat one's a little tricky because it almost has to, when it adds it, it basically is going to add it to the other side of where it is. Okay? When it removes it, it's also going to remove it from the side where it is and kind of move it to the other side. And we'll see a couple more examples of that in just a moment. Okay? Now, let's finish this out with pressure. So, in pressure we're specifically talking about gases, okay? But in an increase in pressure, it's going to cause a shift toward the fewer moles of gas, okay? So we see here in this equation, we have 3 different gases. So on the right-hand side, we have 2 moles of gas. On the left-hand side, we have 1 and 3, so we have 4 moles of gas. So if we increase the pressure, it's going to cause a shift to the fewest number of gases if we increase the pressure. If we decrease the pressure, it's going to cause a shift toward the more moles of gas. Okay? So again, we're always trying to get it back into equilibrium. Okay? Always trying to get it into equilibrium. All right. So let's take a look at this one together. I think I have a little typo here. This should say PCl3. Not sure what happened to me. PCl3. And this one should say PCl5. So make those quick corrections on your page. PCl5 for the first one, and then PCl3 for the second one. So let's look at these together. The addition of Cl2. So here's our Cl2. If we add more Cl2, then it's going to want to work in the opposite direction to balance it out. So that's going to cause a shift in the equilibrium to the left. Okay? Now, the next one, increase in pressure. If we increase in pressure, remember this is having to do with the gas, it's going to go towards the fewest number of moles. So over here on the left, we have 1 mole. On the right, we have 1 mole of gas plus another mole of gas, so we have 2 moles of gas. So it's going to shift it to the fewest. That means it would shift it to the left. Okay? In the next one, it says the removal of the heat. So if we remove the heat, we're taking it out of there and basically adding it to the other side instead. Okay? And so it's going to work against the heat, in the opposite direction of the heat, because the heat's going to fuel it to go the other way. So again, that's going to go to the left. And then the last one, the removal of PCl3 as it forms. So if you take out PCl3, well, we can't not have any PCl3. If we take it all out, we need to start making some more. And so that ultimately would cause it to shift back to the right to be able to make more PCl3. Okay? So that is how you do those. Now, take just a moment and pause me, and then we'll come back and look at these together. So pause now and answer those questions and then restart. So you should have gotten left, left, right, left. So let's talk about these really quickly. So the first one, it says lowering the temperature. So if we're lowering the temperature, that basically means we're taking the heat there, out of there, and we're putting it on the other side, okay? And so then it's going to go away from the heat. So away from the heat is going to make it go to the left, okay, or to the reactants. The next one says increasing the pressure. If we increase the pressure, we're going to want to go where there's the fewest moles of gas. So over here on the left, we have 1 mole of gas. That's the only one that has the G for gas. This is a solid, so that doesn't count. On the right, we have 2 moles of gas. Okay? So we're going to go to the fewest moles of gas, and again, that's going to take us to the one which is on the left, to do the reactant side. The equilibrium is going to shift to the left. On the third one, removing H2. Okay? So if we take that H2 out, the goal is basically going to be to try to make more H2, to replace it, to get back to equilibrium. So that's going to cause it to proceed to the right, or to the product side. And then the last one, if you add H2, okay, if we increase that H2, then hopefully we can use that to increase the production of these guys. And so that is going to shift it away from the H2 and hopefully use that H2 to build some more of the carbon and the water on the other side of the equation. Okay? So hopefully you all got those. You have an assignment today, which is the maze to work through and figure out which way the equilibrium is shifting for that problem. And if you all have any questions, then let me know. And if not, then have a great day.